So to continue our discussion here with the galactic perspective from the telescope is Dr. Mike Werner from JPL. He is the project scientist of Spitzer. And he also notably, I might add, has impersonated the chief inquisitor in the Galileo work by Bertolt Brecht. So he might be known to some of us in that fashion. Here is Mike.
Thank you very much. Okay, it's a pleasure for me to be here today to talk about telescopes and the galactic perspective. Let me just start out by pointing out, as George already indicated, we're in a golden age for telescopes these days. I'll be talking more about the large ground-based telescopes. George mentioned these various telescopes. Singly, I just want to point out that in 1985 or so, there was a vision of what we call the great observatories, these 4 observatories operating together in space, getting to wavelengths inaccessible from the ground, and providing a coordinated capability for exploration of the universe. Right now we have operating Spitzer, Hubble, Chandra, and Compton, which was the original gamma-ray great observatory, has been replaced by Fermi. So this dream has actually been realized. The scientific fruits of it are marvelous, as you can see here. This is a Spitzer in red, Hubble, and 2 Chandra bands image of the Cassiopeia A supernova remnant, seeing everything from the cool dust imaged by Spitzer to the very hot plasma seen by Chandra. And I think right here is a neutron star. So this promise has been fulfilled and realized, and I frankly don't think people have taken adequate notice that this is something that was started over 20 years ago and is now a reality. So what I'm going to do in my talk is talk about telescopic advances in the 20th century which have led to an increased understanding of things in our galaxy. And I'm going to do this by focusing on the people who made these telescopes happen. In my abstract, I rather boldly call these people the modern Galileos. Now, there are a few differences. First of all, I doubt that too many of them will be remembered 400 years from now, and they are rewarded by their peers not with house arrest, but with, tenure, MacArthur fellowships, and even the occasional Nobel Prize, okay? But the real point I want to make is that even when you're dealing with projects of this scope, it's often the ingenuity, energy, insight, and drive of a single person who is important in either making that telescope happen or optimizing its performance. Now, I'm going to talk about a few people who fit that bill. Somebody else giving this talk might talk about a whole different group of people, but I hope the conclusion would be the same, that even in the era of mega science, the individual can matter. It matters very, very much. So the first person I want to talk about here is, let's see, what have I done? I screwed up already. Previous, okay. Is George Ellery Hale. He saw that to make advances you needed bigger telescopes. He was an amazing guy. This is a picture of Hale. This is his masterpiece, if you like, the 200-inch telescope at Mount Palomar. He was a prime mover in the development of the Yerkes Observatory 40-inch refractor, the 2 large reflectors on Mount Wilson, and the 200-inch or 5-meter telescope at Palomar, each of which in its day the biggest telescope of its type. In addition, as he didn't have enough to do, he founded or co-founded the Astrophysical Journal, the American Astronomical Society, and Caltech. And above and beyond that, he was a pioneering solar astronomer in his own right who invented the spectroheliograph and discovered that the sun has a strong magnetic field. Much of this work he did in his own private observatory, which he built in his backyard, which is over in San Marino, about a half a mile from here. And it's interesting because when he was a kid, or when he was in his 20s, he built an observatory in his backyard in Chicago, and that was his road to the success which enabled him to do all these remarkable things. Here are some of the telescopes that he was involved with. This is the 40-inch refractor at Yerkes. This is the 100-inch reflector at Mount Wilson, the telescope with which Edwin Hubble discovered the expansion of the universe. And this is the 200-inch telescope at Mount Palomar in one of these wonderful Russell Porter drawings that we've all grown up with. What have been some of the contributions of these telescopes to the study of galactic astronomy? Well, there's so many I could go on for hours. I've just picked a couple in each case. To begin with, the 200-inch telescope was used by Böcklin and Neugebauer to make the first detailed infrared map of the center of our galaxy. If you recall George's picture of that edge-on spiral galaxy with all that dust, at optical wavelengths you can't see through the center of our galaxy. You can see through in the infrared. In the 1960s, there had been radio observations suggesting there are interesting things going on at the center of our galaxy. Becklin and Neugebauer imaged them in great detail on the 5-meter telescope with an angular resolution of a couple of arc seconds, showing this very dense stellar cluster, which has been the subject of additional study for years and years since then. To let you know what the progress has been, bear in mind that this image, this beam here is 2.5 arc seconds across. In a couple of minutes, I'm going to show you a detailed image of the central 1 arc second of the galaxy, and this will get to this issue of adaptive optics that was asked about earlier. In another example, Sri Kulkarni et al. Used the telescopes at the Hale Observatory. Some of this work was done on the 60-inch to find the first bona fide brown dwarf as a companion to a nearby low-mass star. These images show the starlight that leaked through a starlight suppression system, and this faint guy here is a brown dwarf, which is identified by the wavelength dependence of its emission. A brown dwarf is a star which never quite made it to the major leagues. Okay? It started to collapse. It wasn't massive and dense enough to ignite nuclear burning, but it became visible because the heat of collapse, which was generated in its creation, leaks away, and you can see it in the infrared, basically. Brown dwarfs are extremely interesting. There are about as many brown dwarfs in the galaxy we now know as there are all other stars put together. And based on some work with Spitzer, there's about a 50-50 chance that our nearest stellar neighbor is a brown dwarf, closer than Proxima Centauri. And that may be one of the major discoveries of the WISE mission that George was talking about earlier. So from Hale, I'm going to skip on to the latest generation of large optical telescopes. Both Jerry Nelson and Roger Angel have developed and demonstrated new paradigms for the construction of 10-meter class telescopes. Now, there's other ways of doing this, most notably at the European Southern Observatory, but Jerry and Roger have been the prime movers in important technical developments. Jerry realized that you could make a primary mirror out of segments, but the segments which are off-axis have to be figured to a strange shape, which isn't necessarily easy to do. So he invented the idea of what's called stressed mirror polishing, where you hang weights on the edge of a flat mirror blank to distort it elastically. You then polish a spherical figure into it, which is pretty easy, I guess, for an optician. And then you take the weight off, and it springs back to the shape that it needs to take its place off-axis in this telescope you're designing. That was a brilliant insight, and the Keck telescope is built in that way. Roger Angel has taken a different approach, and with fairly inexpensive Pyrex glass, he's prepared 8.4-meter blanks, put them into what is basically a huge oven, and spun the thing very slowly while applying heat. So the glass, when it melts, becomes viscous and deforms to the shape of a parabola. The 8.4-meter diameter here is set by the spacing of the pillars which are holding up the University of Arizona football stadium. He's doing this work in the basement of the stadium, if you like. And both of these developments have been uproariously successful. They've culminated now in the Large Binocular Telescope in Arizona, which is two 8.4-meter apertures side by side, mounted in tandem. They both point in the same direction. And that's the spin casting, Roger's technique. Jerry's technique, of course, has led to the development of the two Keck telescopes, 10-meter telescopes in Hawaii. Both of these technical approaches are under consideration for incorporation into 30-meter class telescopes. And, of course, it's no coincidence that there are two telescopes in each of these observatories, because they can be used together in an interferometer to enhance the spatial resolution to that which is equivalent to the spacing of the two mirrors. Now, I have an example of the work that's been done with telescopes of this type, which is absolutely astounding. This work has been done by Andrea Ghez. Again, there's a group led by Reinhard Genzel in Europe who's done similar things at the European Southern Observatory. She used adaptive optics at the Keck Observatory to study the motion of stars to the galactic center. Adaptive optics is a technique for correcting the distortions in the wavefront which are introduced by the atmosphere as the starlight propagates through the atmosphere. There are various versions of this, but this is what's called laser guide star adaptive optics, where you project a sodium laser up through the atmosphere. There's a layer of the atmosphere up about 60 kilometers, I think, where there's sodium atoms which return this laser light to you. And if you look at the wavefront of the return light and compare it to the wavefront of the projected light, you can see what's the distortion due to the atmosphere. And the power of this technique, which is really powerful, as George Coyne suggested, is indicated here. This is a view of the central 8 arc seconds or so of the galaxy. You turn your laser on, and all of a sudden you see this, okay? Because all the atmospheric blurring, which has produced these distorted images, is taken away, and your angular resolution is close to the native resolution of the telescope, here at a wavelength of 2 microns. And this is the central 8 arc seconds of the galaxy. And Andrea and her team have figured out how to determine the motions of the stars which are in the vicinity of this object called Sagittarius A star, which we now know had already been indicated, clearly know is a massive black hole, because this now is the central 1 arc second of the galaxy. You can see the motion of these individual stars using this adaptive optic techniques, and you can see that they're swirling around a point which is right there. This is about 10 years of data, and these objects are moving a distance which is roughly a tenth of a light year, and so they're moving at a goodly speed, and they're all orbiting this central object whose mass has been determined with great precision now to be 4 million solar masses. And with a larger telescope, it'll be possible to carry out detailed tests of general relativity. So I'm now going to show a movie of this happening. So this is a movie of 10 years of data. These are the stars swooping around. And all I can say is if that doesn't excite you, you're in the wrong place right now. I mean, that's absolutely amazing. Okay. So that's a little bit of what's been done with optical astronomy. Now let me move on to space astronomy. And space astronomy, again, can be talked about in terms of the contributions of one person, Lyman Spitzer, who was a tremendous astrophysicist, but he also foresaw the development and power of space observatories. And he wrote in 1946 for a RAND corporation report, which I think might have been classified at the time, I don't know, but it was replayed or reprinted in 1990, a paper called Astronomical Advantages of an Extraterrestrial Observatory, where he talks about optical, infrared, X-ray, ultraviolet, all the things that the great observatories now do, and modestly talks with great foresight about new phenomena not yet imagined, open up completely new vistas of astronomical research, which is what these observatories have done. In addition, he was the principal investigator of the first UV spectroscopic explorer, Copernicus, and a tireless campaigner for the Hubble Space Telescope. The telescopes that he was involved with, this is the Copernicus telescope. This, of course, is Hubble, which George talked about very effectively. And it's worth mentioning that Spitzer was helped by John Bacall, who, together with Lyman, were the founding fathers of the Hubble Space Telescope in a turbulent political environment. What are the kinds of things that these observatories have done? Well, Copernicus has gotten very high spectral resolution studies of the diffuse interstellar gas looking through space into a star that radiates in the ultraviolet. And all of these, the broad stuff is the star. All these narrow lines are the lines of atoms and molecules in interstellar space, of which there are about 27 in the spectrum of this particular star, provided new insights into the processes in the space between the stars. Hubble, very notably, has produced this iconic image of the Eagle Nebula, where you can see dynamic sculpting of dense clouds, which will trigger the formation of new stars. And very, very importantly, Hubble has obtained images. This is an image of a circumstellar disk, a disk around a young star projected against a bright nebular background. This is tremendously important, I think, because our whole paradigm of star formation is based on the idea that there are circumstellar disks within which planetary systems form. It's really nice to see a picture of such a disk to tell you that you aren't often in the wrong place. So this is great stuff. Now, in the X-ray band, of course, the key driver is Riccardo Giacconi, whose work culminated in the Chandra Observatory. He won a Nobel Prize in Physics, the first director of the Space Telescope Science Institute, and later the director of the European Southern Observatory. In 1962, he and his colleagues launched an X-ray rocket to find X-rays from the moon. I guess the idea was that something would be hitting the moon and X-rays would be fluorescing. I don't think X-rays have yet been seen from the moon, but in the process they discovered the first extrasolar system X-ray source, and the field of X-ray astronomy was off to a splendid start. The first X-ray satellite was launched by Giacconi et al. In 1970, and now we have Chandra and maybe someday ConX, or IXO as it's now called. X-rays, of course, don't get to the ground. You have to study them from space. And what have we learned from that? Well, again, a bunch of things. One of the more surprising things is that young and forming stars are copious sources of X-rays. This is an X-ray image of a particular cluster. This is an infrared image where you're used in the infrared because stars form in cold and dusty regions to see young stars in the infrared. But you'll notice that all of these objects have X-ray counterparts as well. And the X-rays are somehow produced in the turbulent outer layers of the atmosphere of the star, which is kind of readjusting itself as it's coming together. The presence of those X-rays, of course, has implications for the chemistry of the protostellar matter, protoplanetary matter, which would be in a disk surrounding the star. In addition, there's this wonderful image from Chandra of the pulsar at the center of the Crab Nebula. A pulsar is a rotating neutron star discovered by radio astronomers in the 1960s. This pulsar in the Crab is rotating at 30 times per second approximately. It's producing a wind which is driving the expansion of the Crab Nebula, and you can see the wind, the interaction of the wind with the nebular material in these rings of various size. The pulsar itself is right here. It is certainly not resolved even by Chandra. Moving into the infrared, we'll start back a bit with Bob Layton, a familiar person to all of us from Caltech, who was an amazing guy. First thing he did after he started his research career was he discovered the solar 5-minute oscillations. Many of us might have quit right there. But then he conceived and built the 62-inch spun epoxy primary mirror, the same technique that Roger Angel used, smaller scale for a 2-micron sky survey telescope. Then he went up and led some imaging teams for some JPL spacecraft. And finally, he designed and built precision 10-meter diameter microwave dishes at the OVRO interferometer in the Caltech submillimeter observatory. And when I say he built them, he literally built them. And those of us who've been around for a while remember when what used to be called the synchrotron and is now, before that was where the 200-inch mirror was built, there was a big vertical lathe there that Bob put in, and he had these 10-meter backup structures rotating around and these aluminum panels and a cutting tool. And he made these dishes just like that. And they were really wonderful. So the one at the Caltech submillimeter observatory is the high dish, the precision dish, which achieves good performance at wavelengths as short as 350 microns. Some of the results from Bob's telescopes, well, you have the 2-micron sky survey, which contains thousands of sources, mostly mass-losing evolved stars, which have sort of given us a lot of information about what happens as stars like the sun evolve off of the main sequence where they start their lives. In addition, from the Caltech submillimeter observatory, it's been possible to obtain spectral line surveys to study the complex details of circumstellar and interstellar molecular chemistry. This is a source called IRC plus 10216, which appropriately enough is one of the sources discovered here. And you can see a modest forest of emission lines of molecules of things like HCN and CS and so forth. And then this is the Orion central complex in Orion, where there's a very dense interstellar cloud. And you can see a lot more molecules, things like methyl alcohol, CH3OH, and sulfur oxide and HCl+. The difference, of course, is this is a carbon-rich chemistry because it's in the atmosphere of a star in which the atmosphere is rich in carbon as a result of the evolution of the star. This is an oxygen-rich chemistry, more typical of interstellar matter. But this is only about 10% of the microwave spectrum, and you can see that there's just an amazing number of spectral lines and a very complex and intriguing interstellar chemistry going on. Working with Bob on the 2-micron sky survey was Gary Neugebauer, who worked at the Galactic Center, as I've mentioned, in the 2-micron sky survey, And importantly for us, he headed the U.S. science team for IRAS, which was the first cryogenic infrared observatory in space. To do things well in the infrared, you have to be cold. You have to, in those days at least, up till now, we've always launched either liquid helium or solid hydrogen as a coolant. IRAS surveyed the entire sky in 4 bands in the infrared to unprecedented depth. It was a joint U.S., UK, Dutch project, and Gary was the prime mover on the science team in a way which I'll explain in just one second. Okay. What were the results from IRAS were extraordinary. It really opened up the infrared sky, set the stage for missions like ISO and Spitzer. This just shows the galactic plane as imaged by IRAS. You can see towards the center it's kind of narrow because the stuff is far away. It gets thicker as it gets out closer to us. The blue band, this is cold stuff around 100 degrees Kelvin. The blue band is hotter stuff in our solar system. And this is the IRAS view of Orion. This is the visible light view of Orion. And the same thing in the infrared looks like this, where you see dense clouds of cool interstellar matter and dozens of young and forming stars. The other really important point about what Gary did was that the IRAS catalogs were originally released in hard copy, but the database, with some 250,000 sources, soon became one of the first examples of a well-maintained and supported computerized database available to the entire astronomical community. And it's now the toolkit of every young astronomer who's more computer savvy than I am to be able to cruise or surf through these databases in all kinds of spectral bands. There's a thing called the National Virtual Observatory, which sort of institutionalizes that. And I think a lot of that methodology and the reliability and the utility of these databases can be traced back to the IRAS database, which Gary was instrumental in starting and which was supported here at the IPAC Center that George is in charge of. And finally, our last hero is Frank Lowe, who was another brilliant inventor. He invented the germanium bolometer, the oscillating secondary mirror, which is a tool used routinely by infrared astronomers to subtract the background. He was the first person to do infrared astronomy from high-altitude aircraft. He was instrumental in the development of IRAS, and he conceived the novel warm launch architecture which enables Spitzer. This is a picture of Frank. He died just recently. This is Frank and myself when we went to give him a medal for his discovery of invention of the warm launch concept. And that can be explained very clearly. This is a cartoon he drew of Spitzer with a telescope which would be launched warm, which we could do because of the orbit for Spitzer, and a small cryogen tank which held just enough liquid helium to keep the instruments cold, and then the telescope cooled down radiatively. In previous concept, this cryogen tank would have extended all the way around the telescope and been much more massive and required the use of a cryogenic shake test to verify the launch performance and so forth. So this was a major breakthrough using radiative cooling to support the cryogenic cooling, and future infrared observatories like JWST are using that. I should say that with a small fraction of liquid helium carried by all other cryogenic missions up to this time, the Spitzer cryogenic system outlasted them all put together. We ran out of helium in May, but because of the radiative cooling in the orbit, we're still very, very cold in our Earth-trailing solar orbit and doing exciting work with the warm Spitzer at the toasty temperature of 26 degrees Kelvin. Okay. Here are some of the telescopes Frank worked on. This, of course, is Spitzer with the shields and black paint, which is part of the radiative cooling system. This is the Learjet telescope, where he started his airborne work. When you wanted to work in the Learjet, you had to wear an oxygen mask. And this is the C-141, the Kuiper Airborne Observatory, which replaced that. This is a 1-meter telescope forward of the wing. And hopefully before long, we'll be using an observatory called SOFIA, which carries a 3-meter class telescope in a 747. What science have these observatories enabled? Well, I couldn't resist putting this in, although it's a little bit off topic. The KAO, because you can use an airborne observatory anywhere, you can go interesting places. And in 1977, Jim Elliott and his team went to the southern hemisphere to observe a stellar occultation by the planet Uranus, and by God, they discovered the rings of Uranus, because just before the star disappeared behind Uranus, this is time in this direction, and there were these blips, and then there was a dip when the star went behind Uranus, and there were some more blips, coincident with these blips, but on the other side, it was very clear immediately that rings were orbiting the planet Uranus. This, for some Spitzer contributions, again, I could go on for hours, but first of all, this is a piece of the Orion Nebula in which all of these green dots are objects identified by Spitzer as candidate young stars with protoplanetary systems around them. Probably the most profound result in galactic astronomy in the last 20 years has been the recognition that planetary systems are extremely common around other stars. Our next speaker will be talking about that in detail, but given how common planetary systems are, it's not at all surprising to see lots and lots of potential planetary systems around young stars. If you point your spectrograph with Spitzer at one of these planetary systems, you'll see this amazing spectrum, which is rich in lines of acetylene, hydrogen cyanide, carbon dioxide, and everything else is water. This is the data, this is the model, okay? And so you can actually see the stuff of life, if you like, being incorporated into a potential planetary system in the spectrum of this young star. And perhaps Spitzer's most remarkable achievement was the first measurement of light from planets around other stars. There are enough planets known now that some fraction of them actually move behind their star as we observe them. And because these planets tend to be warm and big and close to the star, they have an appreciable infrared signal. So here you're seeing the infrared light from the planet plus the star. Temporarily, the planet disappears. This contribution is the infrared radiation from the planet itself. And Spitzer has now done this for numerous stars. The Kepler mission launched not long ago, of course, will discover many such eclipsing stars, and we'll be helping them follow up on them. And Giovanna Tonetti here in a minute is going to talk about what's been learned by studying these transiting planets. So, what are the characteristics of these Galileos of the 20th century? And beyond the obvious one of being either smart, very smart, or really, really smart, okay? And it occurred to me, although I don't know enough about them, I expect that many of these characteristics were shared by Galileo. First of all, they have to be technically excellent and ingenious. They have to know how to do things, how to fix things, how to invent things, how to make things work, and how to use them most effectively. They have to be opportunistic, as Galileo was. Often the opportunity is presented by technology, as George was saying. They have to be able to seize that opportunity when it's right and run with it. They have to be visionary, as Lyman Spitzer was when he talked about, observatories that he wouldn't live to see and how powerful they would be. They have to be evangelical, not in the religious sense, but because I couldn't think of a better word to describe the fact that they have to be galvanized, not in all cases, of course, but many of these people effectively led big teams. They didn't do all this themselves, but they have to have the ability and the personality and the magnetism to galvanize other people into action and to get them to work together effectively. They have to be ambitious and driven. I doubt too many of the people that I was talking about earlier worked 40-hour weeks. And I think maybe the most important thing is they have to be uncompromising. And anybody who worked with Neugebauer or Frank Lowe know that they were uncompromising. They were never satisfied unless things were being done the best possible way, and they expected the very best, not only of the people that worked with them, but they themselves as well. So this is kind of the recipe. Now, I'm not going to say too much about the future of galactic astronomy. I think the key elements are going to be high spatial resolution and high spectral resolution to pursue the kinds of things I talked about. But I think the most important thing is to make sure we have a system in which people with these characteristics and these desires can help us to achieve our scientific objectives. Remember, science is not a democracy, and we have to allow the leaders and the people with the best ideas and the best vision and the best energy, we have to make sure there's a way for them to have their voices heard and their efforts and work recognized. Now let me go back and talk about the topics I've talked about. I've taken them and rearranged them slightly. So this is now an evolutionary sequence. So remember, we just started with diffuse interstellar medium. That was the work of Copernicus and Lyman Spitzer. So suppose you start a life as a hydrogen atom here. Well, somehow, perhaps due to the rotation of the galaxy and density waves and stuff like that, you would find yourself in a dense interstellar cloud of the type we talked about with the Eagle Nebula in some of the Spitzer, the IRS images. And in a dense interstellar cloud, if gravity builds up, you can get young and forming stars. We talked about those in the context of IRS, Spitzer, and remember Chandra, somewhat surprisingly. These stars we now know frequently have protoplanetary disks. We know that they very often have exoplanet systems, and of course, it's likely, I think at least, that many of them will give birth to life of some kind. In addition, we talked about the brown dwarfs, which are sort of an unsuccessful stub off the young and forming star tree. Now, right here is where a star spends most of its life, right, on the main sequence. Haven't talked too much about that. That was still a very interesting scientific focus, particularly as people get more and more interested in exoplanets. But then we talked about the evolved stars undergoing mass loss, studied by the 2-micron sky survey and studied by the CSO. And we talked about supernova remnants and neutron stars, which are the end of this process, okay? Well, what's happening here, of course, is that this stage and this stage are returning to the interstellar medium, returning up here, material which has gone through those stars and in many cases been processed so that whereas it was so there's more heavy elements or a different mix of heavy elements in those next generation of stars than there was in the previous generation of stars. And this cycle of conversion of interstellar medium into stars, chemical enrichment, and returning is basically the main cycle that drives the evolution of our galaxy. Occasionally you get a brown dwarf or a neutron star which steps out of the dance, and stars are long-lived in here, but there have been several or maybe many cycles of this giving rise to the chemical complexity and evolution of the galaxy and making the stardust from which life might arise. And of course, when we look at other galaxies, what we're seeing is just the same effect going on a much, much larger scale. So 100 years ago, I don't think too many of these things were understood or known about. We now study in great detail with the telescopes I've talked about each of these stages individually, as well as the interesting and important transitions between them. In addition, we talked about the center of the galaxy, which is of great interest not only for its own characteristics, but because of the active galactic nuclei, which are found at the center of many nearby galaxies. We talked about massive black holes, which are also extremely interesting from the point of view of other galaxies because of the fact that it's an amazingly and relatively recently discovered fact that basically every galaxy has its own massive black hole at its center. And that's understanding what that means and how it came about is a puzzle for the next decades. So this just illustrates the fact that understanding our own galaxy is really important if we want to understand other galaxies as well. And so let me just close with another multi-wavelength image provided the great observatories' unique views of the Milky Way. And you can see how fortunate we are to live in this era of a telescopic renaissance. Thank you very much.
One question before we break.
Hi, Mark. How does the dark matter and dark energy observation come into picture?
Well, okay. Fortunately for me, and I think George will agree, the stuff in our galaxy, I mean, it's in the configuration it's in because of the influence of dark matter and dark energy. But I think the stuff the processes that are going on that I talked about are pretty much immune from dark energy and dark matter on a day-by-day basis. Now, the one thing where there might be some effect is that there's a question as to whether I talked about this process by which more and more matter is locked up into stars. Well, if there's more matter falling into our galaxy to replace that matter that's being tied up, it's a different situation than if we're in a closed system and we're just using up all of our stuff. And I think there have been discussions certainly about continued infall from the intergalactic medium, and I'm sure if there is such an infall, it's mediated in an important way by the dark matter halo. I mean, there's no question that our galaxy has got a dark matter halo, but those particles just sail through us and don't have too much effect on the detailed processes I've talked about.
Let's thank Mike again.
Thank you.